right, today we're going to finish up chapter 3 with a pretty straightforward section, and then we'll look at the first part of chapter 4. So remember, when you're solving a system of equations, that generally means you're solving for a minimum of 2 variables. It could be more, but a system is when you have to solve for at least 2. We're going to look at systems from a graphical perspective. And if we're going to graph it on the calculator and solve it, what do you think we're going to look for once we put something in y1 and then put something in y2? We're going to look for what?
Intercept?
Yeah, we're going to look for an intercept. And we're going to be looking at equations that might not be easy to solve with like elimination or substitution. All right. Remember, when you write your solution to a system, okay, especially if you just had 2 variables, the answer is a coordinate. When you solve a system, you have to tell me an x and a y value. If you only tell me x, then you've only solved for 1 variable. You haven't solved for the other one. So when we're solving a system graphically, as Julie just said, we're going to calculate the point or points of intersection on the graphs. And there can be a lot of them, right? And you have a lot. Think of like a circle and a parabola. You know, something like that, it could cross 4 times. So you get 4 different solutions. So when we're solving a system, we have to find all of them.
What would happen if like the lines like ran on top of each other for a while and then separated?
Lines can't do that. Because the only way, they can't run on top of each other for a while and then separate, because they're either always on top of each other because they have the same slope, or they're only going to cross at one point. So lines can't do that. The only way you could do that is with like a piecewise function. If you drew like a line with a certain slope for part of it, and then you drew a different line and changed your slope, that would be a little different. But yeah, we won't have anything like that. That's a good question. It might look like lines are on top of each other for a while, like that, but they really only cross in one spot. They're just really, really close. This kind of system is called an unstable system because these 2 lines are so close together that if you just change the slope of one of them a little bit, you can move where they cross a lot. Okay, just by, if I tilted this line down a little bit, I could move that intersection point way over there. All right, so let's solve that graphically. This is one we could do with substitution and elimination, but how am I going to have to rewrite that to be able to put it in on a calculator? I can't put that in. Yep.
In like slope intercept form?
Yeah, so ideally we want what variable alone?
Y.
Yes. So the top one would become y equals, let's see, we would have a negative 2x plus 5, and each one of those would get divided by 3. And the bottom one, somebody tell me what that one would be?
3/5 x plus 21/5.
Yep. So you'd add the 3x and then divide by 5. So 3/5 x plus 21/5. A little annoying with fractions to have to type these in, but we're just going to use parentheses. So let's do negative. What I'm typing in is exactly the same thing, just parentheses to clarify. So negative 2/3 x plus 5/3 and 3/5 x, 3/5 x plus 21/5. All right, so let's hit graph, and we're looking for where they cross. All right, so that's a good, perfect window. That's just the standard window. Second calc intersect. And you can write your answer a couple different ways. You could write it just like this. X equals -2, y equals 3. Or as a coordinate. You can write it either way. Any questions on that one?
Are you zoomed in on that?
Am I zoomed in? No, I think that's just the standard window. Yep. -10 to 10, all that stuff. All right, this one is not asking you to find the solutions, so let's not waste time finding them, just how many there are. Right? So let's type this in and see what we get. -x cubed plus 3x squared plus x minus 3. And -2x squared plus 5. Is there anything before it? No. All right. And I still am using the standard window. So, how many solutions are there to this one? Caleb?
2.
I don't think so.
3.
Yeah. So we always have to check for stuff that goes off the screen. And I think if you set the y min at like -30, you'll see that, maybe that's low enough, but I think you'll see that they are going to cross again. Not quite. I can go lower. We're not trying to find it, but I think you can see they are going to cross again. Okay. So the answer here is 3 solutions. And that's a little tricky. So you always have to look for answers that go off the screen like that. Okay. So 3. Any questions on that? Yeah.
Is it the biggest exponent? Like, is the amount of times across?
No, not necessarily, because we're combining different kinds of graphs. So we can take a circular graph, which has actually has like a square root function in it, and a parabola, which has an exponent of 2. And when you graph those, they cross 4 times. So you can't go by the highest exponent necessarily. Because I could also have a cubic and a quadratic that look like this. That's what this could have looked like, and they only cross once. So I could get 1. I could get 2 out of it. Maybe if I thought about how to sketch that, maybe I could do something like this. Now I get 2. Or in our case, we get 3.
Is there any possible way to get imaginary crossings, intersections?
No, because when you're looking at it graphically, you're only looking at real answers. So, could there be imaginary solutions? I don't think so. I'd have to think about that a little bit more, but we're only focused on the real solutions in this section anyway, because graphically that's all you can do. All right, and let's finish up with this one. Solve graphically and algebraically. Okay, let's do it algebraically first. How would I solve this algebraically? What would be the easiest method to use on this system? Yep.
You just substitute in.
Yeah. I would substitute because we know y equals x cubed minus x. So substitute that in for y. X cubed minus x equals 3x. And using the methods that we've been using, what number do we always try to get on one side? What do we try to get on one side to be able to solve this or do rational root theorem or any of that stuff? So think about when we do rational root theorem, we're solving for the roots, which means we're solving for the numbers we can plug in for x that give me 0. So you always want to get 0 on one side, and maybe we'll use rational root theorem to solve this. I don't know. So x cubed minus 4x equals 0. But what's always easier if you can do it? And we can avoid rational root theorem and synthetic division. Yeah.
Quadratic one.
If you have a quadratic, you could. But we don't have a quadratic in this case, so we can't use that formula here. Yeah?
Factoring.
Factoring. How can you factor x cubed minus 4x? This is a simpler kind of factoring. It's not a complicated one. Yep.
You can pull out a Graphically factor back.
All you can do is pull out a GCF. Now, I have a difference of 2 squares. How does x squared minus 4 factor? Yep.
X plus 2, x minus 2.
Good. X plus 2, x minus 2. So my answers to this problem for my x values are 0, -2, 2. So I'm going to write it like this to make it clear. 0, -2, 2. But what else do I need to still find? Yeah?
You just find the y values, make sure that the solution is normed, correct?
Yeah, I've only done half the problem. Well, the y value is easy. Just pick any formula and plug the x's back in. I think the bottom one is the easiest. To get the y value, triple the x value. Okay? So that should be a solution. That should be a solution. And that. Let's graph that and confirm what we just did.
Oh, that makes a lot of sense.
Yeah, I actually think this one is faster this way than graphing. All right. So now I need to type in x cubed minus x and 3x. I don't have a very good window, so let me do zoom 6. This is why I think graphing can be slower. All right, so 0, 0, yep, I see that one. -2, -6, +2, +6. Those all look good to me. So 1, 2, 3. Any questions on that? All right, we got lucky to solve that one. That wasn't actually too bad because of all the factoring. It worked out nice. This could have been a lot worse where you have to do the P's and Q's, get the rational roots, then use synthetic division. But not in this case. All right, any questions on 3.7? Okay, so chapter 3 was all about polynomials. Chapter 4, we're going to start off by looking at what are called rational functions. So a rational function involves 2 polynomials, and you divide them. So here's a polynomial in the top. Here's another polynomial in the bottom. That is what you call a rational function. So with polynomials, remember we said the domain was all real numbers. Now we're talking about rationals. Rationals have fractions. What value are you not allowed to end up with in the bottom of a fraction? John?
0.
Can't end up with 0. So just to make this a little easier to think about, if you had a problem like the one I have on the board, -6, something weird is going to happen there, right? And we'll talk about what happens. Your bottom, and this is what I basically just said, your bottom polynomial can never equal 0. Okay. There's an example of a rational function. X squared plus 1 divided by x minus 3. Not going to do anything with that right now. Just, that's an example of a rational function. Okay. There's another rational function. 3x squared minus 4x plus 1 divided by x squared plus x minus 2. This one's pretty easy to figure out what you can't use for x. You can't use 3. This one would be a little bit more complicated, but still doable. You'd have to solve for the roots, just like we learned in chapter 3. Find the values of x that you could plug into this that make it come out to 0. How do you solve for the roots? Well, easiest case scenario, that would be factorable. Worst case in this one, quadratic formula. And if they come out to imaginary roots, then we don't have to worry about saying they're not in the domain. Okay? We're only really worried about real numbers when we're talking about domain. Okay, so domain of rational functions. It's all real values, as I just said, except the ones that would cause the denominator to be 0. We just spent a whole 2 or 3 sections talking about how to find values of x you can plug in that make it 0. So we have all kinds of ways to find them. So let's find the domain of this one. Anyone tell me the domain of example A? Yep.
All real values except for 3.
All real values except 3. So I'm going to think of it this way. Here's a number line. I'm going to think of it as having a hole at 3, just like that. And it includes everything this way and everything this way. Does anyone remember as an interval how you write, we'll call it part 1? John?
Negative infinity with parentheses and then comma 3 with a bracket after.
Bracket means to include 3.
Oh, then parentheses.
Parenthesis. So that's part 1. How do we write part 2 of the domain? Mabel?
3 with a parentheses and 2 positive.
To positive infinity. Anything else I need there?
And
The U, right? Union means or. So it's every number from negative infinity to 3, not including, or 3, not including it, to infinity. Okay? So there is our domain for that one. Let's look at this one. So what do we have to focus on here when we're trying to find the domain? Is it the numerator or the denominator? Caleb?
Denominator.
Denominator. And we want to make sure that the denominator is never what?
0.
0. So let's set it equal to 0. Let's solve for what would make it 0, and then say the domain is everything except that. See if we can factor it. Let's see. Is that going to be factorable? I think so. Somebody tell me. Yeah?
It would be x plus 2, x minus 1.
Let's check. X squared minus x plus 2. Perfect. Perfect. So, domain is all, let's write this one a little different. All reals except what values? Yep.
negative 2 and 1.
-2 and 1. If you wanted to do this one using the notation we had before, you'd think of it like this. Whole, part 1, part 2, part 3. We'd have to break it into 3 parts. Everything less than -2, not including. Between -2 and 1, not including either endpoint. 1 to infinity, not including 1.
Do you put a U between each
Yep.
one?
You'd have 3, yep, you'd have two of the U symbols. Right, and this one I'm going to skip writing it down. Let's just say it verbally real quick. Well, what are the 2 values you can't use in the domain here? Yep.
2 and -4.
2 and what?
-4.
-4. 2 and -4. It's really just like B, except it's even easier because they already factored it for you. Okay. So the simplest rational function you can have is this one. The other ones I showed you guys, those are more complicated. That's the simplest. 1 over x. And what value are you not allowed to use for x in this case? Bless you. Yep.
0.
0. So we know something weird happens at 0. Bless you.
Actually,
And there's your graph. What happens as x approaches infinity? What does y approach? And it's going to be the same answer as x approaches negative infinity. What does y approach? Julie?
0.
0. Because think about what happens as this number gets huge. Plug in 1,000 for x. You get 1/1000th for y. Plug in 1,000,000 for x. You get 1/1,000,000th for y. So the bigger the x value you have, the closer to 0 you are approaching. Now, will you ever reach 0?
No.
Or what if you plug in 1,000,000,000,000? Still not 0. It's 1 divided by a huge number, which is never 0. The only way you can make a fraction 0 is if 0 is in the top. Well, the top is a constant value of 1. That's never going to be 0. So this fraction will never hit 0. But it'll get close. And if you are getting closer and closer to something without ever reaching it, that is called an asymptote. Asymptote. So in our case, we have an asymptote, which I'm just going to put in as a dotted red line. Usually asymptotes are dotted, but it's a dotted line at y equals 0. It's kind of hard to see, but I did put in a dotted red line, and you can see the blue line never actually reaches it. I run out of pixels, so eventually it looks like it reaches it, but it never does. So the way you find a horizontal asymptote is you examine what happens to your function as x heads to the right or to the left forever. Now, the example I had up above, our graph, well, you tell me, does the graph ever cross the asymptote? It never does. And on the left is another example of a graph that has asymptotic behavior because it's getting closer and closer to a horizontal line. And it never crosses it. Now, the one on the right is an example of something with an asymptote, but it does cross it. It's okay to cross an asymptote as long as you are getting closer and closer and closer and closer to something as you approach infinity or negative infinity. Okay? In this case, as you approach infinity, you're getting closer and closer to, maybe that's 4, I don't know. Right? But you are getting closer and closer. Yes?
Are there vertical asymptotes?
Yep, we'll talk about those soon. But yes, they are vertical. You can also have a graph that does something like this. That would be considered an asymptote. Because what's happening is the graph is approaching this value as you head towards infinity, but it never stays right on it. It's oscillating around it. It's still asymptote. Okay? Most of the time when we look at asymptotes, they're going to look like that, though. They're not going to cross a lot. They might cross like one time near the origin, but as you head left and right, it's going to approach a value. Okay, and page 217's got some more pictures. So, let's find the horizontal asymptote of this. Now, what was the asymptote of this one?
0.
It was 0. And does anyone remember from when we studied the transformations? What does adding a number at the end do to a function? Yeah? It shifts it up 2. So if you know that this shifts the graph up 2, everything is shifted up 2, including the original asymptote. So it was y equals 0. Now the asymptote is y equals 2. If you didn't know that, you can definitely just graph it. You can look at it that way. And you can see you are approaching 2. Or just think about it algebraically. Plug in a big number for x. Okay, plug in 1,000. 1 divided by 1,000 is 0.001. It's 1/1000. Plus 2 is 2.0001. If you plug in 1,000,000, you're going to have 1/1,000,000 plus 2. Very, very, very close to 2. Okay, so you're getting very close to 2. How about this one? What would your horizontal asymptote be here? Yep.
Y equals -3.
Yep, y equals -3. If you look at this part as x approaches infinity, I like to say this part disappears. Because you're going to be dividing it by something so big, it's going to become so small, it basically doesn't even matter. So y equals -3. Questions on that? Okay. I'm not going to sketch this. You can graph it on the calculator, but the idea here is I wanted you to understand, which we already did when I asked you guys. This would shift it up 2. And we didn't say what the other one would do, but how would a -3 shift it? John?
Down 3.
Down 3. Yeah. So some graphs can have 2 horizontal asymptotes, okay, at the same time. So the way we look at a problem like this is we break it into cases. Okay, we're going to break it into cases. And a lot of times we end up using long division, okay, like we learned in chapter 3. So let me show you an example of a graph that has 2 horizontal asymptotes. Now, remember, when we're trying to find a horizontal asymptote, you really want it to be written something like this. Which doesn't even have to be a 1 here. That's kind of the format you're looking for. You could have a number in front of the x, that's fine. You could have a number in the top, that's fine. And you can have plus or minus a number at the end. But that's the general form that you want to get it in. Just like you see right there. Okay. So, let's look at this one. Since it has an absolute value in it, absolute value causes different behavior between negatives and positive numbers. Okay? If you have an x value that's already greater than or equal to 0, what does absolute value do to a number that's already greater than or equal to 0? Yep.
Doesn't change it.
Doesn't change it. Doesn't do a thing. So if we look at this problem from the case where we always have an x value that's greater than or equal to 0, you don't even need the bars. So that's going to be case 1. I'm going to divide that synthetically very quickly, because when I do synthetic division on this, it's going to turn it into the format that I want. So let's do that. So you divide by the number after the minus. So that would be x minus -3. And in the numerator, 1, -2. Bring down the 1. -3 times 1, -3, -5. That's my remainder. So we can write this as, let's see, 1x minus, let's see, my remainder over, I'm sorry, that's just 1. This is my quotient, and it's a constant. It's not an x. Sorry. 1 minus my remainder over my original denominator. That's what you get when you divide those using synthetic division. Now I can actually see there's 3 transformations. We're not going to talk about it right now, but it's a vertical stretch by a factor of 5, a shift up 1, and I have this plus 3, which is inside the function. That's going to move it left 3, which for our problem wouldn't really matter. Okay, so that's the first one. Now, let's think about the case when x is less than 0. What would you have to do if you have a number less than 0 and you want to take the absolute value of it? What would happen to it? Always had a number less than 0. Yes.
Positive.
And how would you make it positive?
How far away is from here?
Well, what arithmetic would we have to do to make it positive? What would be the operation? Yeah?
Plus or minus? No.
Explain to me more what you mean.
Like to make it positive, we would have to bring it out and then say plus or minus something.
I'm thinking some kind of arithmetic. If you know you always have a negative number, what do you do to the number to make it positive? Because that's what absolute value is going to do. Yep.
Multiply by -1.
Exactly. Make it the opposite. If you always know you have a negative number and you're taking absolute value, make it the opposite. So in case 2, the numerator would stay exactly the same. But effectively, if you had a number less than 0 and you want to take the absolute value of it, you're doing that. You're making it the opposite. Because we already know it's less than 0, and by making the opposite of it, it would become positive. So let's divide that out and see what we get. All right, so let's see. When we divide that, okay, we want to think of this. You know, we haven't done the long division in a while. Let's practice that one. What do you get when you divide negative x into x? Negative 1. Multiply it back out. What's negative 1 times x? Yep, x. And what's negative 1 times 3? Negative 3. And remember, subtract your columns. That's gone. What's negative 2 minus 3? 1. So it's very similar to what you get up above. Negative 1 plus my remainder over my original denominator. All right. Now, let's look at each of those. As x gets really big in this fraction, what happens to what I circled in blue? Let's pretend you plugged in 1,000 for x. What would that number in blue come out to? Yep.
That's small.
Very small. And approaching what? Approaching 0. So basically what I've circled there is going to approach 0 when x gets really big. How about here? What does that approach when x gets really big? Yep.
0?
Also approaches 0. Pick a big number, like 1,000,000. 1 divided by negative 1,000,000 plus 3. It's negative 999,997 or something. It's 1 divided by a huge negative number. It's going to be very small. So all that's really left is this and that. And those are your 2 horizontal asymptotes. All right, so let's graph that so you guys can see that we have 2 horizontal asymptotes. All right, so x minus 2 divided by, in parentheses, math, number, absolute value, x plus 3. Now, let's think about it a little bit. This was the case when x gets really, really, really big, right? X is greater than or equal to 0. So as we head to the right, we should notice the graph approaching 1. As we head to the left, we should notice the graph approaching -1. And let's see. And we do. Let's even make it a little bigger. Let's go -25 to 25, and -3 to 3. So you'll notice as you head to the right, easier to check on the table, but the bigger the value you put in, the closer and closer that number is approaching to 1. When I head to the left, plug in something like -500, it's approaching -1. So the way to do a problem like that is to really split it into cases and think about it as two separate problems, because that's really what absolute value is. There's really two separate rules for absolute value. Positive numbers, absolute value does nothing to the problem. You could get rid of it. Negative numbers, it makes it the opposite. So that's why we had case 1 and case 2. And whether you use log division or synthetic division to break this out, you really need to have it written in the format I showed you. You've got plus or minus something over here, and this is usually the y asymptote. This part always disappears because it has an x in the bottom, and anything with an x in the bottom heads to 0 as it gets bigger and bigger. Okay? So that's why I divided it out the way I did. All right, so now let's think about something a little bit different. I don't want to think about what happens as x gets bigger and bigger and bigger. Let's think about what happens as it approaches 0. If you plug in a number like 0.0001 for x, what happens? Yeah?
The fraction gets larger.
Yeah, you get a huge result, right? If you type this in, it's easier to do it quickly on the table. But let's plug in like 2. Okay, we get a half. Let's plug in 1. We get 1. Let's plug in 0.5. We get 2. Let's plug in 0.1. Now we get 10. 0.01. We get 100. 0.00001. We get 10,000. So as x approaches 0 from the positive side, that means heading that way. As you approach 0 from the positive side, your y value increases towards infinity. That means it increases without bound. This is the notation for writing as x approaches 0 from the positives. Positive means from the right. How about as we approach 0 from the left? Meaning coming from the left side and heading towards 0. What does f of x approach in that case? That's like plugging in -2, -1, -0.1, -0.0001. Getting closer and closer to 0 from the left. Nick?
Negative infinity?
Yeah, that approaches negative infinity. And any time you have this type of behavior, this is what we call a vertical asymptote. So someone asked about that earlier. This is the behavior that occurs near a vertical asymptote. So, in general, you always write the equation of a vertical asymptote as x equals a number. A horizontal asymptote is always y equals a number. If I give you a multiple choice question on a test and I say, what is the vertical asymptote? I would probably put some choices in there that are x equals, and I would put some choices that are y equals. You need to know which one is vertical. So, x equals h is considered to be a vertical asymptote if, as you approach h, either from the left or the right, and asymptotes can also be one-sided, okay, like this. That's called a one-sided asymptote because there is no graph on the left side. So you can't approach 0 from the left, it doesn't exist. But you can approach 0 from the right. So x equals h is a vertical asymptote if, as you approach h from either the left or the right, your graph either goes up forever or down forever. Now, remember, if the numerator and the denominator have no common factors, the way you find the vertical asymptote is where the denominator is 0. What happens if you have a numerator and a denominator with a common factor? You don't end up with an asymptote. What do you end up with in your graph? John?
Straight line.
Um,
Or not, sorry, I thought you meant the same number. Not
it's a type of discontinuity. What do you end up with if the numerator and denominator have a common factor?
The steps.
You don't end up with steps, but we did talk about it the day we did that. Yeah?
Little holes.
A hole. Okay, you can end up with a hole in the graph instead of an asymptote. So in a problem like this, let's say x plus 2 over x minus 3, there's a vertical asymptote at 3. In something like this, there's no vertical asymptote in that problem. Yes, 3 would make the denominator 0, but it would be a hole in the graph. It would not be a vertical asymptote. Okay, so what would be the vertical asymptote in this problem? Next. 2. That's the value that would make the denominator 0, and there are no common factors in the numerator. What would be the equation of the vertical asymptote in this case?
You need the,
Yeah.
thank you.
Yep. Yep.
2,
Uh,
3.
no.
There's something. No, it would be.
Where the denominator is 0.
Oh.
Negative 3.
Oh.
How about now? What would be the vertical asymptote?
Negative 3.
Negative 3. How about now? Shifting up and down does nothing to the vertical asymptote. Only thing that affects that is if you shift left and right. Okay. I've already kind of touched on the shifting. So I think this is, yeah. All right, so let's look at this one and describe the behavior of it, and then we'll probably save the mixture one for tomorrow. I'll probably go over that when we do the homework. We've kind of done mixture problems before. This is an easier mixture problem, but maybe what I'll do is I'll put it in the video after you guys leave so you can still see it, but I'm going to do it again for homework when we go over it. Okay, so we want to describe the transformations here. This isn't written properly. How did I rewrite the absolute value one so I could see it properly? What did I use? Nick?
Synthetic.
Yeah, I use synthetic division. So let's do that. So put the 5 on the outside. Let's put a 2 and a negative 13. These are very short synthetic division problems. Bring down the 2. 5 times 2 gives me 10. And what's negative 13 plus 10? Negative 3. Let's set this up. Quotient plus, or in this case minus, remainder over denominator. So let me go through in general what these numbers mean. put this right here. Okay, so this is adding or subtracting inside the fraction. That's your horizontal shift. This is adding or subtracting outside your fraction. That's your vertical shift. This is multiplying in the top part of the fraction. That would be a vertical stretch. This is multiplying inside, right next to the x. Usually the x is second, I'm sorry. Like 3x or 2x. And that would be a horizontal stretch. It's exactly the same as when we studied parabolas. So, horizontal asymptote in this case, y equals 2. We've shifted up 2. What would be my vertical asymptote? John? 5. That's the 0 of the denominator. Now, describe the transformations. Remember the order we always start with. Start with your horizontal shift. Which way has this graph moved?
It's moved, what is it, to the left 5, and then up 2.
Let's see, it's going to be shift, it's a minus, so that's going to move it right. Because our vertical asymptote moved 5 to the right. Okay. Is there a horizontal stretch in this one? No, it's a 1. Next thing we look at is the vertical stretch. Is there a vertical stretch? By a factor of how much? 3. So vertical stretch by factor of 3. And what's the last thing that we do? Well, actually, vertical stretch by a factor of 3, and think of it this way if you want. What does a negative do when it's next to the vertical stretch? Flips it. So everything we've done is right, I just didn't want to forget that one. That negative causes a vertical reflection. And the last thing, what does the plus 2 do? Yep, which way? Yep, shift up 2. Okay, so remember, if the number with the stretch is negative, it causes a flip with it. So we can take a look at another one of those when we go over homework. And I'll do this one after you guys leave. It'll probably take me about 3 minutes. So I'll go over this when we go over homework. So the first part of the homework is on 207, that's graphing. And the second part is 222. Okay, when you get to the mixture one on 222, if you get stuck on it, don't worry too much about it. But I think the mixture one is number 48. We'll take a look at that together. Okay, so in the last part of the video, I'm going to go back to the problem we didn't get to, which is the mixture problem. And we're going to focus on finding what's called a concentration, which a concentration measures basically how strong a solution is. So let's look at this example. If you had a 50-ounce solution, and I told you that 35% of the solution actually contained acid in it, some kind of chemical. Okay, in this case, it's an acid solution. The way you figure out of the 50 ounces, how many ounces are actually acid is to take 50 ounces and multiply by the percentage that's acid, which in this case is 35%. So 50 times 30.35 gives us 17.5 ounces of pure acid. So the rest of the solution might just be water, okay, or something that's diluting it. All right, so we have 17.5 ounces of pure acid. So in our example, we're going to take the same solution we had up above, and we're going to add X ounces of pure acid to the... Okay, so whenever we're figuring out the concentration of a solution, you want to think about the following formula. Concentration equals amount of, in this case, acid divided by total. Okay, so amount of acid divided by the total amount of liquid altogether. So, in our problem, we're going to add X ounces of pure acid to our 50-ounce solution. So, find a graph of the new concentration. So, the amount of acid that we have. Well, we know that we're already starting with 17.5 ounces of pure acid, because we had a 50-ounce solution, and there's 35% acid out of the 50 ounces in it. So we're starting with 17.5 ounces of acid, and it says that we are going to add X ounces. So that will be the amount of acid we have. Okay, so in the numerator, we had 17.5 ounces of acid to start with, and we just added X ounces of pure acid. Now, the denominator is going to represent the total amount of solution. Well, we know we're starting with 50 ounces, because that's what the problem said, and we're pouring in X ounces of liquid into that. So this is going to represent our new concentration. So let's graph that and see what it looks like. So we've got 17.5x plus x, divided by 50 plus x. And let's think a little bit about the window. So we know we're not subtracting liquid, so we don't have to worry about negative x's. Let's say we add up to 150 ounces. Okay, we can technically add as much as we want. And the concentration, well, if the concentration started at, let's see, it originally was a 35% solution, the concentration can't go any lower than that, because all we're going to do is add pure acid to make it stronger. So the minimum concentration is 35%, and the maximum the concentration can approach is 1, but it will never reach it. That's because you always had something in the mixture that wasn't pure acid to begin with, so no matter how much acid you add to it, it'll never be pure acid. It's kind of like if you had red paint and you had a little bit of blue mixed in. If you add more and more and more red paint, it might hide the blue, but the blue is still going to be in there. You'll never get pure red paint if you had something other than red paint in it to start with. So let's look at our concentration, and you can see the concentration increasing the more acid that we add. And now they want to know if we wanted to get a concentration of 75%, how much acid would we have to add? So we're going to graph 0.75. That's a concentration. And we're going to calculate the intersect, just like we learned in the last section. So if you add 80 ounces to the existing solution, you will end up with exactly a 75% solution. All right, so that's how you do the mixture problem. And again, for those watching it, if we didn't get to go over it in class, we'll take a look at it again when we do the homework. And there is the homework again.